Good afternoon, everyone, students and all. Welcome to this session where we will go through just one topic in Pure Mathematics, Unit 1. My name is Mrs. Dixon Campbell, and I will be your presenter today. So let's go right into the subject. Now, the objectives for this session are: one, we will look at an overview of pure mathematics. Then we will go through an introduction to reasoning and logics, where at the end of the lesson, you should be able to identify simple and compound propositions. You should be able to establish the truth value of compound statements using the truth table. And then we should be able to answer some exam type questions on this topic. So let's go. Now, what is pure mathematics really about? Here are the requirements that we will need to do this subject. You will have to have CSEC mathematics, preferably at a range 1 or a range 2. But the plus to do pure mathematics is having additional mathematics, whether it is grade 1, 2, or 3. That will give you the perfect start to do this subject. Now, the syllabus is going to be very important for this subject. So I would advise you to go on the CXC website and download the syllabus so that you are able to follow the topics that your teachers will go through with you. Now, the internal assessments, your IAs, this will be in the form of a test. So you'll have 3 tests to cover. These 3 tests will come from the 3 modules that are in this subject. All right, so that's really a brief overview of what the subject is about. Now, let's get into one of the first topic on your syllabus, reasoning and logics. This is an introduction, so I expect that as we go along, you will be able to understand and be able to maneuver CSEC CAPE questions as we move through this topic. Now, reasoning and logics is about circuit building circuits. And if you are an electronic student or an electrical student, the word logics would probably pop out at you. If you are also a physics student, you'll be able to somewhat relate to some of the things we will discuss in this topic. Now, as you see this stoplight here, logics and reasoning helps in the building of these circuits, in maintaining and building these circuits when the light should go. And so we don't have 2 sides having the red at the same time, etc. Computer games, softwares, these all come under reasoning and logics. And of course, as I mentioned before, if you would have done electronics or electrical, you would have probably heard of the gates, the AND gate, the NAND gate. And you will bring that knowledge also into pure mathematics, as these subjects are interrelated. Now, logics will involve propositions. You'll hear this word, it's nothing to be alarmed about. Propositions are really statements, just as in English language, where you have propositions, right? These are statements, and these statements may be true or false. Can you think of a statement, a simple statement? All right, let us look at some examples. The sun is hot. That's a statement. Is it true or false? It is still a statement. It is raining now. Now, where you are, it might be raining or it might not be raining. However, it cannot be raining and not raining at the same time. So that is one category of a statement that we should establish here. A statement can't be true and false at the same time. Another statement is, today is a holiday. Simple statement. The product of 2 and 5 is 7. And everybody might be saying, oh no, that is not correct. Well, remember how I started. A statement does not have to be true. It can be true, it can be false. So here, this statement obviously is a false statement, but it is a statement nevertheless. Another statement, it is snowing in Mandeville now. And when I say Mandeville, I mean the Mandeville in Jamaica. All right, again, this might not be true, but it is a statement. These are examples of what we call simple propositions or simple statements, just as I said in English language. Now, in mathematics, these simple statements can be represented by letters. So if I want something to do with my simple statements, I don't have to be writing the statement every time I make mention of that statement. So I can call it statement P, statement Q, etc. So we use letters to represent our statements. Now, logics will also involve negating propositions. And that means making the proposition the opposite case, making the sentence the opposite. That's what negating a proposition is about. So for example, if we want to negate the proposition, today is a holiday, if I want to make that the opposite, what do you think the new statement will be? The opposite statement of today is a holiday. Well, if you would have guessed it, today is not a holiday would be the opposite. And that is the negation of the original proposition of today is a holiday. All right, and I know some persons might be wondering, is this an English class or is it mathematics? Trust me, it is pure mathematics. We will get into the logics of it very, very soon. Another example, if I want to negate the proposition, 5 is an odd number. What's the opposite of 5 being an odd number? The negation is 5 is not an odd number, or 5 is an even number. Those are opposites. All right, so the original case was 5 is an odd number. That is the statement. Now, the opposite statement, the negated statement, the negated proposition is 5 is not an odd number. It's as simple as that. Now, symbolically, as I mentioned earlier, we could use letters to represent our statements. So, if my statement is called P and I want to negate P, I can write this by using a little tilde. For those who know Spanish, you would have seen tildes before. As I said, everything is interrelated. We use a little tilde with the letter, and that represents the negation of the statement. All right, so that's our first symbol to note here, the negation symbol, a little swirl with the letter representing the statement. Now, compound statements or compound propositions. If we're talking about simple statements, and I will use the word statement and proposition interchangeably, but in this case, they can be used interchangeably. All right. So don't be alarmed when you hear me say statements or if I say proposition. Okay. Compound propositions. Now, if you, just as in English, if you have simple statements, you also have compound statements, and we also have it in pure math. Now, a compound proposition, just as in English, it's when two or more simple statements or propositions are joined by connectives. All right. Now, you can think of some of the connectives that we use in English, right? English and math goes hand in hand. The subjects are interrelated, right? So think of some of the connectives that we could use in English when we are combining simple statements or simple sentences. All right, have you thought about them? So we could have and. So the boy is big and he likes to run. So we join two simple statements and make it into a compound statement. We do that in math. So let's just look at some examples here of the connectives that we use. So in mathematics, just as in English, we have our connectives that we can use to connect simple statements, two or more simple statements. So the main connectives are the not, which we spoke about, the negation, all right? And please make note of the symbols that we use to represent these connectives. So we have the tilde, as I mentioned before, to represent negation. Next main connective that we use is called the conjunction. The conjunction is also called the and connective. And the symbol that we use to represent the conjunction looks like an upside down V. Or you can use the capital A to help you to remember that this represents the conjunction connective. All right. Next connective that we have is the disjunction, also called the or connective. And of course, this symbol looks like a V. All right, so please make note of these symbols as we will be using them throughout our compound statements. Then we have the implication, also called the if-then connective. That symbol is an arrow pointing to the right. All right, so we have seen the negation, the conjunction, the disjunction, the implication. And as we go through, we'll get used to these terms. Lastly, we have the biconditional, and this is the if and only if connective. All right, and as you hear the word bi, it means two. So you'll see the arrows pointing in two directions. All right, that is the if and only if connective. So we have 5 main connectives that we use in pure math to combine two or more simple statements to make a compound proposition or a compound statement. All right, we're still in math. We're still wondering, is this math or English? It is definitely math. Not to worry, we're getting there. Now, let us continue with some more compound propositions. Now, as I would have mentioned before, you can use letters to represent your statements. So we can use symbols to represent our compound propositions. Now, let's say, for example, P is the statement, I am fat. And Q is the statement, I am beautiful. Now, the compound statement, I am fat and I am beautiful can be written as, now I don't know if you remember the symbols that we used a while ago, but as I said, we need to know these symbols so we can represent our statements. Now, it's going to be as simple as P and Q. So we have the P, you have your symbol representing and you have your Q. So the P represents the statement, I am fat. You have your symbol representing and you have your Q for the statement, I am beautiful. So instead of this long compound statement that has 1, 2, 3, 4, 5, 6, 7 words, you can just have 3 symbols representing the compound statement. Let us look at another example. So the compound statement, and we're still using P to mean I am fat, and we're using Q again to mean I am beautiful. So the compound statement, I am either fat or I am beautiful. And this can be written symbolically as, you get a go at it. It's as simple as P or Q. Remember, this symbol looking like a V represents the or connective. All right, and we'll continue. The other compound statement, if I am fat, then I am beautiful. All right, so here you are seeing that the connective that is being used here is the if-then connective, the implication connective. And do you remember how that one looked? It was an arrow pointing to the right. So symbolically, this compound statement can be represented as P implies Q. P implies Q. If P, then Q. If I am fat, then I am beautiful. And here's another statement. I am beautiful if and only if I am fat. All right, so the connective that is being used here is the if and only if connective. That's the biconditional connective. And if you remember that symbol, it has 2 arrows. Remember the biconditional, one pointing to the left, one pointing to the right. So here is how it is represented symbolically, right? Not bad at all. We're getting there. Now, I want you to do this for me now. I want you to write the compound statement. I am not fat and I am beautiful. I am not fat and I am beautiful. Go ahead and try that one. I'm just going to give you a few seconds. I am not fat and I am beautiful. All right, let us see if you have gotten that one correct. There you'll have it. Because of the word not, we have to negate, or we have to make it the opposite. So P was the statement, I am fat. So the opposite of I am fat is I am not fat. So that's why we had to negate the P. And of course, we have our and connective. So we have our symbol representing the and we have our simple statement, I am beautiful, which is represented by Q. Quite easy, I would suppose, not as challenging so far. Now let us look at another example. So we are given two statements. And you will see me using P and Q quite often, but P and Q are not the only letters that can be used to represent statements. Other letters can be used, but for the sake of this presentation, I'm using P and Q as the letters P and Q are normally used frequently on your CAPE examinations, but other letters can be used. So here we have two statements. P being, I do not love mathematics. That's a simple statement. And another simple statement, Q, I will pass pure mathematics. So we have two statements there. Now, what would this mean in words? Not of P and Q. What do you think that means in words? Not P and Q. So I want you to go ahead, think about it. Not P and Q. We want it in words, not symbols, words. So this is the opposite of what we are doing from a while ago. Okay, so here is the answer. I love mathematics and I will pass pure mathematics. So let me just explain quickly. Now, not of P, the negation of P is actually the opposite. So if I do not love mathematics, the opposite of I do not love mathematics is I love mathematics. And of course, this symbol here represents the and connective. So we have the word and in our compound statement. And of course, Q is I will pass pure math. So the compound statement now is I love mathematics and I will pass pure mathematics. All right, let us continue. Now the truth table. Is this the table where everyone tells the truth? Let us see. This tells the truth value of a statement. This tells if their statement holds true, how true it is when you actually look at all possible combination or all possible scenario of your statement. So let's go deeper. Now, if you would have recalled earlier, I mentioned that a statement can be true or it can be false. Now, in our truth table, we use the letter T, capital T, to represent true. And in some books, they use the number 1, and we will use F for false. And some books will use 0 to represent false. For this presentation, I will be using the T and the F. Capital T for true, capital F for false. Now let's look at the truth table for the not statement. So we have different truth tables for the different connectives. So let us look at the not statement. Now, you want to have all the possibilities for a statement. So if I have a statement P, that statement can either be true or it can be false. All right, so if I want the not of that statement, the negation of that statement, if the statement is true, remember the negation is the opposite. So the opposite of true is false. And if that statement is false, the opposite of false is true. So this represents the truth table for the not statement. So here's something to help you with. So this is the rule for the not statement. The not of a statement is just the opposite of the statement. So whatever it is, The not of it is just the opposite. And this is one of the simplest truth table for the connectives. Let us look at the other connectives. The conjunction, the and statement. So let us look at two simple statements. Let P be, the grass is green, and let Q be, it is raining. So let us consider the statement, P and Q. What does that mean in words? The grass is green and it is raining. So you are told that the grass is green and it is raining. So you go outside, the grass is green and it is raining. Let us look at the validity of that statement, how true that statement is, using our truth table. All right, so before I go any further, I need us to pay attention here where we have 4 combinations here for our true and false statement for the 2 statements. So what this means, T means that it is true that the grass is green, and T here means that it is true that it is raining. Now, we want all possible scenarios. So we want all the combinations for true and false. Now, one way to ensure that we have all combinations, and I will tell my students this, if I have 2 simple statements, that means I have 4 possible scenarios of true and false, 4 combinations. And that is when both statements are true, when the first statement is true and the second statement is false, or when the first statement is false and the second statement is true, or when both statements are false. So we want to test the validity of this statement. We want to see how true it is, and we want it for all scenarios. All right, so you have 2 truths for the first, 2 false for the second, for the two true, 2 false, and then for the second statement, 1 true, 1 false, 1 true, 1 false. When you do it like this, you have all combinations. Rather than sitting down and trying to remember to see if you have all combinations, this is the good way, or this is the best way to actually ensure you have all combinations of true and false. Now let us continue with the and statement. So again, you were told the grass is green and it is raining. Now, suppose you went outside and you see that, yes, it is true that the grass is green, and it is also true that it is raining. Then our original statement is correct. However, on another day, you realize that the grass is green, however, it is not raining. That will make our statement false because we were initially told that the grass is green and it is raining. So it's happening together. So if you realize that one is happening and one is not happening, that means that our statement was false. And again, if you realize the grass is not green, but it's raining, that means our original statement was false. And if you see that it is not raining and it is not, the grass is not green and it is not raining, then our original statement is false. All right, so here's a little tip to help you to remember the and statement. Both values have to be true for the result to be true. Otherwise, the statement is false. So for the and conjunction, both statements have to be true for my original statement to be true, for my and statement to be true. All right. Let us look at the or connective. the disjunction. Again, we will look at the same two simple statements. The grass is green, it is raining. Let's consider the compound statement. The grass is green or it is raining. So that's original. That is my statement. I am told that the grass is green or it is raining. Let us look now at the truth table. Now, again, we have all possible combinations here in the first two columns. We have two truths, one true, one false, one false, one true, and when both are false. So the or connective says that it is true that it is raining. It is true that the grass is green. So then our statement is correct because our original statement says the grass is green or it is raining. So yes, it's a possibility for the grass to be green as well as it is raining. Now let us look at the second scenario. The grass is green, but it's not raining. Was my original statement true? Yes, because we were told that the grass is green or it is raining, right? Let us look at the other scenario. The grass is not green. Here the F tells me that it is false. So it is the grass is not green. However, it is raining. Is this a possibility in our original statement? Yes. It is possible for the grass not to be green, but it is raining because the original statement says the grass is green or it is raining. All right. Now, here in the last row here, the grass is not green and it is not raining. Then our original statement would have been false. Because again, the original statement says the grass is green or it is raining. So can you come up with a little rule for the or statement, the disjunction? What do you think governs this or statement? So here is a little rule. At least one value must be true for the result to be true. Otherwise, the statement is false. So if you look at your table here, at least one true is here for it to be true. At least one true is here for it to be true, right? However, in my last scenario here, we have no true here. So that's why it is false. All right? So these little rules can help you to remember how your truth table should be for the or statement. Let us look at another connective. Now the implication, the if-then statement. Now this one is a little bit more challenging, and so the examiners tend to like to ask questions about this connective. So let P be the statement, the grass is green, and Q be the statement, it is raining. So let us consider the statement. The grass is green implies that it is raining. How else can we say this statement? If the grass is green, then it is raining. Let me say that again. If the grass is green, then it is raining. So, can the grass be green and it's not raining? No, because the grass being green is dependent on it raining. So let us say that statement again. The grass is green implies that it is raining. All right? So where the focus here is the grass being green. It doesn't matter if it's raining or not. But as long as the grass is green, then it should be raining. It must be raining. All right. So let us look at this truth table. Again, we have all possible combinations of true and false. When both are true, when the first is true and the last is false, when the first is false and the last is true, and when both are false. Now remember, the statement is, if the grass is green, then it is raining. Or the grass is green implies that it is raining. Or if the grass is green, then it must be raining. All right, that is my statement. So let us check this out. So here we're seeing that it is true. So this is a scenario that it is true that the grass is green. And it is also true that it is raining. So then my original statement is correct because the grass is green while it is raining. Next, let us look at the other statement. Now you see here that the grass is green. However, it is not raining. This cannot be true. It must be false because our original statement says that if the grass is green, then it must be raining. Right? And we're seeing here that the grass was green, but it's not raining. So that means that our statement is false. Now, if we look here, we see that the grass is not green. However, it is raining. And that is a possibility. Because it doesn't matter if it is raining or not. The truth of the matter is, if the grass is green, then it must be raining. Right? So it doesn't matter if it's raining or not. The fact is, if the grass is green, then it should be raining. So this is also true. This is also a possibility. And lastly, the grass is not green and it is not raining. Then this is fine. This is a possibility. All right. So let us remember this connective, the implication. If the grass is green, then it is raining. So the grass being green is dependent on it raining. So if it is not raining, then the grass don't have to be green. And that's why our last scenario is true. All right. So this truth table here is very important. All right. Now, the final connective. Let us look at the truth table for the if and only if statement, otherwise called the biconditional. And I hope we remember how that symbol looks, right? It has the arrow pointing in two directions. We will still use our two statements. The grass is green, it is raining. So let us consider the statement. P, if and only if Q. All right, so this is telling me that the grass is green if and only if it is raining. Again, we have all combinations here in the first two columns. So we have two true, first true, second one false, first one false, second one true, and when both are false. Now, P, if and only if P, if and only if Q, sorry. Now, for this connective, we will see here that for it to be true, if you let us look at the truth table for the biconditional. The grass is green, and we realize here that it is raining. So here is the condition that the grass is green as well as it is raining. So yes, my original statement is true because my original statement says, if the grass is green, if and only if it is raining. Now here you see that the grass is green. It's not raining. So therefore my statement would have been false. And the third one, the grass is not green, but it is raining. That is a false because it is saying once it is raining, the grass should be green. And in my last scenario, the grass is not green, it's not raining. So therefore this statement, this scenario is a possibility. This scenario is true because once it is raining, the grass is green. Once the grass is green, it is raining. It goes two ways. All right. What do you think is the rule for the biconditional connective? I'm giving you a chance to come up with it. All right. So here is a little rule to help you. Both values must be the same for the result to be true. So we would have seen here, you have the same true, so the result is true. Down the last scenario, both are false for it to be true. So we have little rules to help us to remember how to set up our truth tables. Now, all this takes practice for us to get used to how the truth tables are drawn. We are expected to draw these truth tables for different scenarios as we go along. Now, let us look at some exam type questions. Now, here we go. Let P and Q be two propositions. They ask us to construct a truth table for the statements. So they want one truth table to show these two statements, these two compound statements. Now, if you look here, they want the P implies Q. The P if Q. All right. Again, you have to make sure you have all possible combinations of P and Q. Now, I just want to pause here to say that we can have more than two statements. So in pure mathematics, we can go up to 3 statements. And for your homework, I want you to come up with how many combinations of true and false we can have for 3 statements. So when we have 2 statements, there are actually 4 combinations, as you would have seen coming right along. Now, so here for this example, we have all scenarios. 2 truths, first one true, second one false, first one false, second one true, as well as both of them being false. So we have all combinations of true and false. Now we're going to see what happens for the P implies Q. Remember, P implies Q means if P is going to happen, then Q must be happening. Let's say that again. If P is going to happen, then Q must be happening. So the P implies Q is, it is true for P, it is true for Q, so our statement is true. Remember the implication says, once P is happening, and the order here is very important. It's important to look at the P first because P came first in our compound statement. So the second scenario here, we see that P is happening. However, Q is not happening. So that must be false, right? The third scenario said P did not happen. However, Q was happening. So my statement is true here because that's a possibility, because the implication says as long as P, the first one, as long as P is happening, then Q must be happening. It doesn't matter. Q can do anything it wants. However, once P is happening, then Q must occur. And finally, P did not happen, but at the same time, Q was not happening. So that is also a possibility in my scenario. So that is part one of that question. Now, here is the other part that's worth 2 marks. Now, this is the not of P and Q. So now here we are seeing brackets in logic. Now, just as in mathematics, when you can recall BOMDAS, where you work with the bracket first. So we need to see the scenario of what's happening in the bracket, the P and Q. So we need a column for P and Q first. Now, if you remember the rule behind the and connective, both has to be true for us to get a true. So here, P is true and Q is true. So of course we have a true. Now, if you look at the other 3 combinations, we are not having 2 truths. Hence, we have false for that result. So this is the P and Q truth table. However, the question asks us for the not of P and Q. What are we going to do? They want the not of all of this. And if you can remember, the negation is just the opposite of our statement here. So the not of it is just the opposite. So the opposite of T is, the opposite of true is false. The opposite of false is true. Opposite of false is true. And the opposite of false is true. And that's it. 3 marks there. And I just want to remind you, 3 marks can be the difference between a grade 1 and a grade 2. 3 marks can be the difference between a grade 5 and a grade 6. All points, all marks are critical. All right, here's another question. Let P and Q be any 2 statements. They want us to copy and complete the table to show the truth table for, again, we are seeing P implies Q, and we're seeing not Q implies not P. So they gave us this table, it's incomplete, and we need to fill in these spaces. All right, again, you would have seen they have all the combinations for P and Q. Now they want us to fill in this part for the not of P. All right, and remember the not of P is just the opposite, the negation of P. All right, so here we see the not of P, just the opposite. So the not of true is false. The not of true is false. Not of false is true. And the not of false is true again. All right, simple. They want us to fill in the not of Q. So what do you think we should have here? You have to make sure that you're looking at the correct column, and we want the not of it. There you have it. So you look at your Q here, the Q column, and you just do the opposite, and you'll have the not of Q. Then now they want the P implies Q. And as I stated before, this particular connective is very important. Now we're going to look at the P and we're going to look at the Q. So we have all these columns going on, but for this particular answer, we are going to need we are just going to look at the P and the Q. So if you would look here, remember for the implication, if P is happening, Q must be happening. All right, so P is happening here and Q is also happening, so you know that's a true. However, you see P is happening, but Q is not happening, so that's a false. For this scenario, P did not happen. So when P is not happening, it doesn't matter what is happening with Q, right? But you saw that Q is actually happening, so that is a possibility. And lastly, again, P did not happen, sorry. So therefore, and Q was not happening, so that is also a possibility. So you have true, false, true, true. And finally now, they want not of Q implies not of P. All right, so it's gonna be important to look at which column first and which column last. So we need to look at the not Q first and then the not P. So the order for this is very important. So we're gonna look at the not of Q, then we're gonna look at the not of P. So you're gonna see here that not of Q is not happening. All right, but when you look here, this is not happening. So this is a possibility. So that part is gonna be true. Now, if you look here, the first one is happening. However, the last one is not happening. Remember, we're looking at the implication, if-then statement. And this is not possible. Because remember, if the first one is happening, then the second one must be happening. All right? For this one, or the first one is not happening. So it doesn't matter what is happening here. So this is a possibility. So this combination is true. And lastly, you will see that the first one is happening and the second one is also happening. So this is a possibility. So hence the answer is true, false, true, true. All right, and that would be 4 marks right there. Now, if you would look at this table here, what would you notice about these last 2 columns? There's something significant about them. Now, I want you to do a little research for me to see what kind of statements or what does it mean when 2 columns are identical in their truth values. All right, so that's it for us today. So we looked at simple statements, we looked at the connectives, so we can make compound statements. We also looked at the truth tables, and we looked at some exam type questions. So I hope that this is a nice introduction for you. Feel free to go ahead and explore questions and practice. Be safe now and hit those books because school is on. All right, enjoy the rest of your evening.